In today's class, we will continue our study of transform coding. Transform coding is a block quantization approach. It exploits the statistical correlation between the samples of the source output vector. The goal of the transformation is to obtain the uncorrelated transformed coefficients and compact the energy into a few of these coefficients. We have also seen that the mean squared reconstruction error is equal to mean squared quantization errors. Now, because these transform coefficients are uncorrelated, it is reasonable to quantize these coefficients independently according to their individual statistical characteristics. Now, the next logical question is that if we are given total number of bits, then how do we allocate the bits to these various quantizers so that the mean square reconstruction error is minimized with the constraint of the given fixed average bit rate. So, this is optimal bit allocation problem, and the definition would be as follows. Assuming that T is an n by n orthonormal matrix, what is the mean squared error optimal bit rate allocation strategy assuming independent uniform quantization of the transform outputs? In other words, what is that set of rate for the quantizers which will minimize average reconstruction error for fixed average rate? Now, the solution to this, let us say that the kth element of the transformed output vector y has variance sigma squared y k. So, we will have set of variances for the different transform coefficients. Now, we have shown that with uniform quantization, the kth quantizer error power is given by the following expression. This we proved it in the last class, where R k is the bit rate allocated to the kth quantizer output and where gamma y k depends on the distribution of y k, that is the kth transform coefficient in the output vector y. Now, we make the simplifying assumption that gamma y k is independent of k. Now, because we are using orthonormal transformation T, this implies that the mean squared reconstruction error equals mean square quantization error, and therefore, we can write mean square reconstruction error as 1 by n summation of mean quantization errors from different quantizers, and this can be rewritten using this expression as y by n, where we have assumed that gamma y k is independent of k and is equal to gamma y. Now, Therefore, we have the constrained optimization problems as minimize this quantity over the set of R k such that we have this constraint satisfied. Now, using the Lagrange technique, we first set differentiation with respect to R L of the following quantity equal to 0 for all L. Now, we can write 2 raised to minus 2 R k as e raised to log 2 minus 2 R k equal e raised to minus 2 R k log 2. Using this relationship, the 0 derivative implies and this implies R L is equal to minus half times log to the base 2 of the quantity lambda divided by minus 2 n sigma squared y L log 2 for all L. This is equation number 2. Hence, R equal to 1 by n sigma k R k can be rewritten as minus 1 by 2 n summation over k of the quantity log 2 lambda is 2 n sigma squared y k log 2, and this can be rewritten as minus half log 2 lambda minus 2 n log 2 plus 1 by 2 n summation k log to the base 2 sigma squared y k. So, from this we get this quantity, that is minus half log 2 lambda minus 2 n log 2 equal to R minus half log to the base 2 product of the variances. So, now rewriting 2, we get R L is equal to minus half log 2 lambda minus 2 n log 2 plus half log 2 sigma squared y L. So, now plugging in this expression into this, we get R L equal to R minus 1 by half log 2 1 by n plus half 2 sigma squared y L, and this can be simplified as shown here. So, this is the final expression which we get for R L. So, the optimal bit rate allocation expression is meaningful only when R L is greater than or equal to 0 and practical only for integer numbers of quantization levels or practical values of R L for a particular coding scheme. So, practical strategies typically set R L equal to 0 when 3 suggests that the optimal R L is negative. Round off positive R L to practical values and iteratively re-optimize the set of R L using these values until at all R L we have practical values. Now, plugging this equation 3 into equation 1, we find that the optimal bit allocation is given by. So, now plugging equation number 3 into 1, we find that optimal bit allocation implies sigma squared q L equal to gamma y 2 raised to minus 2 r Now, what this equation means is that with optimal bit allocation, each coefficient contributes equally to reconstruction error. Now, recall a similar property of the Lloyd-Max quantizer. Now, another algorithm that uses estimates of the variances in a recursive algorithm is as follows. First, we compute the variances for all the transform coefficient. Next step, we set all R L equal to 0 and set R T equal to n times R, where R T is the total number of bits available for allocation among all the n quantizers. Next step is to sort the variances. Suppose the variance for the jth transform coefficient is the maximum. Then the next step is to increment R j by 1 and divide the variance by 2, and next step is to decrement R t by 1. Now, if R t is equal to 0, then we stop, else we go to step number 3. Now, at the end of this algorithm, the transform coefficients with higher variances will be allocated more bits. Now, having discussed the optimal bit allocation, let us discuss the performance of transform coding in comparison with pulse code modulation. So, let us find out how much gain do we get over pulse code modulation. Gain over pulse code modulation of transform coding. Now, with an orthonormal transform and the optimal bit allocation as given by 3, the total reconstruction error equals So, this means total reconstruction error for transform coding is equal to 1 by n times summation sigma squared q L, L is equal to 0 to n minus 1, and this is equal to gamma y times 2 raised to minus 2 r times n minus 1 k equal to 0 sigma squared y k 1 by n 4. Now, compared to uniformly quantized PCM, we have the quantization error equal to reconstruction error for PCM is equal to gamma x sigma x squared 2 raised to minus 12 r, where we are assuming the same fixed average bit rate. Now, since we are using an orthonormal transformation, this implies that sigma x squared is equal to 1 by n times summation over k equal to 0 to n minus 1 of sigma squared y k. So, using this, we have the following gain over PCM. So, gain of transform coding over PCM is given by this expression is equal to this, and this can be rewritten as gamma x by gamma y times arithmetic means of the variances of the transformed coefficients, and this is the geometric means of the variances of the transformed coefficient. gamma x by gamma y accounts for changes in distribution which affect uniform quantizer efficiency. For example, if the choice of the transform T converts uniform PDF x to become Gaussian PDF yk, then this factor gamma y by gamma x would contribute a 7 dB loss in transform coding to PCM performance. Now, we can show this, it is not very difficult, but we will not do this at the moment. Now, if on the other hand x was Gaussian, then yk would be also Gaussian, and in this case gamma y by gamma x would be equal to 1. Now, in literature, this term out here is also known as transform coding gain, and it is denoted as GTC. This is transform coding gain, and this transform coding gain is a measure of the amount of energy compaction afforded by a particular transform, and the efficiency of a transform depends on how much energy compaction is provided by the transform. So, indirectly GTC provides a measure of the efficiency of a transform. Now, coming back to this expression, if we ignore the effect of transform choice on uniform quantizer efficiency, that is gamma y, then this expression 4 suggests that transform coding reconstruction error can be minimized by choosing the orthogonal transform T that minimizes the product of coefficient variances. It is to be remembered that orthogonal transform preserve the arithmetic average of coefficient variances. So, the next question is, what is that optimal orthogonal transform which will minimize this quantity? So, before we try to answer that, let us discuss some of the properties of an autocorrelation matrix. Say that R is an n by n autocorrelation matrix of a real valued wide sense stationary discrete time stochastics process. Now, the following properties are associated which are useful with this autocorrelation matrix. Autocorrelation matrix denoted by R is symmetric and Toeplitz. What it means that R is equal to R transpose, while a Toeplitz matrix has equal elements on all diagonals. The next property is that R is positive semi definite. What this implies is that X transpose R times X is always greater than or equal to 0 for any real valued X. The next property is that this autocorrelation matrix has an eigen decomposition. It means that R can be written in this matrix form, where this matrix V is an orthonormal matrix, which implies V transpose V is equal to I, and the columns of this matrix are eigenvectors V I of R. So, V can be written as and this is a diagonal matrix whose elements are the eigenvalues lambda I of R. So, matrix is equal to diagonal lambda 0, lambda 1 up to lambda n minus 1. The eigenvalues of R are real valued and non-negative. And finally, the product of the eigenvalues is equal to the determinant of the matrix, and the sum of the eigenvalues is equal to the trace of the matrix. This denotes the diagonal element of the matrix R. Now, let us define the outer product as follows. Y 1 m, y 0 m, y 1 squared m, so this is a dot product of the vector y with itself. Now, using the notation to denote the kth diagonal element of a matrix A, we can write equals so the product of the variances is equal to the product of the diagonal elements of this output autocorrelation matrix. Now, this is always greater than or equal to the determinant of the matrix Now, this can be rewritten as because y is equal to t transformed on K. Y is equal to transform T operating on the vector x. So, this is equal to where we are using the fact that determinant of orthogonal transform transpose operating on matrix A is equal to the determinant of the matrix A is also equal to determinant of the matrix obtained by multiplying A and orthonormal transform T. So, based on this relationship, we have gone from this step to this step. Now, this is equal to I because T is an orthonormal matrix. This is equal to the input autocorrelation matrix, and this is equal to again I. So, this implies that this is equal to n minus 1 k equal to 0 eigenvalues of the autocorrelation matrix are x. So, thus minimization of this quantity would occur if equality could be established at this point. So, say that the eigen decomposition of the autocorrelation matrix of x n, which we denote by R x, is R x is equal to V x. For orthonormal eigenvector matrix V x and diagonal eigenvalue matrix shown here. So, now if we choose the transformation T equal to V x transform, then this will result in the desired property. The equality would be established at this point, and this transform is known as Kahrun-Loew transform, or in short KLT. This is also known sometime Hotelling transform or principal component analysis. Now, if we choose this, then the desired property is satisfied, and this can be easily verified as follows. Is equal to expectation of V x transpose times x transpose m V x, and this is equal to V x transpose R x V x, and this can be rewritten as V x transpose. R x can be decomposed as V x times the diagonal matrix composed of eigenvalues times V x transpose V x. Now, this is equal to I, this is equal to I, and therefore, this is equal to. So, in summarization, the orthogonal transform matrix T minimizing the mean squared reconstruction error has rows equal to the eigenvectors of the inputs n by n autocorrelation matrix. The variances of the optimal transform outputs are equal to the eigenvalues of the input autocorrelation matrix, and the optimal transform outputs are uncorrelated. This is a very important result. So, the presence of mutually uncorrelated transform coefficients supports our approach of quantizing each transform output independently of the others. Now, if we have the source output vectors as Gaussian, then the transform output will be also Gaussians, and KLT will decorrelate this components, and for Gaussian case decorrelation also implies independence. So, let us take a simple example and obtain the KLT transform for a particular autocorrelation matrix. So, let us assume that we have Gaussian input with the autocorrelation matrix given as follows. Where rho indicates the correlation coefficient between the adjacent samples. Now, we can obtain the eigenvalues of R x by solving the characteristic equation R x minus lambda I, determinant of this equal to 0. So, if we do that, we get 1 minus lambda rho 1 minus lambda equal to 1 minus lambda squared minus rho squared equal to 0, which implies 1 minus lambda equal to plus minus rho, which implies lambda equal to 1 plus minus rho. Therefore, there are two eigenvalues, 1 plus rho and 1 minus rho. So, for the eigenvalue given by 1 plus rho, we can obtain the corresponding eigenvector V 0 as follows. Is equal to which implies and this implies V 0 1 is equal to V 0 0. So, both the components of the eigenvectors V 0 are equal. So, similarly, for the eigenvalue lambda 1 equal to 1 minus rho, we can obtain the eigenvector V 1 equal to V 1 0, V 1 1 as a solution of the following equation. And this implies V 1 0 plus rho V 1 1 is equal to 1 minus rho V10 rho times 0 plus V11 equal to 1 minus rho times V11, and this implies V11 is equal to minus V10. Now, we also require that the KLT transform matrix should be orthonormal. So, which implies is equal to 1 and V10 squared plus V11 squared is equal to 1, and this implies V0 is equal to 1 by root 2 1 1, and this implies V1 vector is equal to 1 by root 2 1 minus 1, and therefore, the KLT transform for this case is equal to V x transpose is equal to V0 V1 is equal to So, using the KLT and optimal bit allocation, the error reduction related to PCM can be found out for this case is given by this expression. Here we are assuming that gamma y by gamma x is equal to 1, because our input is a Gaussian. So, if we evaluate this is equal to 0.6 for rho equal to 0.8, and this is equal to 0.98 for rho equal to 0.2. Now, the goal of the optimal orthogonal orthonormal transform is to maximize the ratio of arithmetic mean of the variances of the transform coefficients to their geometric mean. That is, we try to maximize GTC, which is by definition equal to the arithmetic mean of the variances of the transform coefficients to the geometric mean of the variances of the transform coefficient. Now, this ratio attains its minimum value equal to 1 when all these variances are equal for all k, and this ratio takes on much larger values when the difference between the variances is large, or we could say the dynamic range of the variances is large. So, although the KLT is an optimal transform in the sense that it maximizes GTC, it is not practical in most circumstances. So, what is the problem with KLT? So, the problem with the KLT is as follows. The KLT maximizes GTC, that is transform coding gain, but is a function of the input statistics. So, what it implies that specifically the KLT equals to eigenvector matrix of the input autocorrelation matrix. Now, unfortunately, realistic signals are non-stationary. So, what this implies that the autocorrelation function will be function of time, and this implies that the autocorrelation matrix will change with time, and this will result into continual KLT redesign if optimality is to be preserved. Now, eigenvector computation is computationally intensive, especially for large n. Now, another problem is that the autocorrelation is computed based on the source output, and this is not available to the receiver. So, either the autocorrelation matrix or the transform itself has to be sent to the receiver. Now, this overhead can be significant, and it itself may negate any gain obtained by using the optimum transform. So, the question is, are there fixed orthogonal or orthonormal transforms that do a good job of maximizing the transform coding gain for typical input signals? And fortunately, the answer to this question is yes. Many transforms have been developed and discussed in the literature in the context of different application. For example, there are popular transforms like discrete Fourier transform, Walsh-Hadamard transform, Haar transform, slant transform, discrete sine transform and discrete cosine transform and many more. Now, for Markov sources with high correlation coefficient between the adjacent source output samples, it has been empirically proved that the energy compaction ability of the discrete cosine transform is very close to that of the KL transform. And now, in practical application, many real sources can be modeled by Markov sources with high correlation coefficient, and this is the reason why discrete cosine transform is so popular transform, because its performance is very close to that of KL transform for most of the applications. And discrete cosine transform forms a part of many international standards including JPEG, MPEG and H.261. Now, except for the scaling factors, Walsh-Hadamard transform matrix consists of only plus and minus 1, and similarly the Haar transform matrix consists of only plus minus 1s and zeros. So, from the computational point of view, these transforms are very efficient, but wherever sufficient computational resources are available, discrete cosine transform is the transform of the choice. Now, the choice of a transform is dictated by the following considerations. One is basically its decorrelating properties in a particular application, the computational requirement for the forward and the inverse transformation, and the size of the transform. Now, as far the size of the transform is concerned, it is dictated by practical consideration. In general, the complexity of the transform grows more or less linearly with the size of the transform, that is n. Therefore, beyond a certain value of n, the computational costs overwhelm the marginal improvements that might be obtained by increasing n. Now, in most real sources, the statistical characteristics of the source output can change abruptly. Like in speech signals, there could be abrupt transitions from the voice period to the silent period or vice versa, or in images we could have abrupt transitions between smooth regions and non-smooth regions. So, if n is large, that is the size of the transform is large, then the probability that the statistical characteristics change significantly within a block increases, and this generally results in a large number of the transform coefficients with large values, which in turn leads to a reduction in the compression ratio. So, let us summarize our study of transform coding. Transform coding consists of three main steps. First step is to divide the data sequence into block of size n. This size is dictated by practical considerations, and in image coding application usually the size chosen is 8 by 8. Now, each block is mapped into a transform sequence using a reversible mapping in the form of an orthonormal transform. Though KLT is an optimum transform in the sense that it maximizes transform coding gain. It is not practical in most of the circumstances, and discrete cosine transform performance is very close to that of KLT, and that is the reason why it is so popular in practical application. The next step is to quantize this transform sequence according to the statistical characteristics of this individual transform coefficients. Now, the quantization strategy used will depend on the three main factors: the desired average bit rate, the statistical characteristics of the transform coefficient, and the effect of distortion in the transform coefficient on the reconstructed sequence. And the final step is to deploy entropy coding on this quantized transform coefficients in the form of some binary encoding techniques like runtime coding, Huffman coding, and arithmetic coding. Now, at the receiver we have the reverse operations. We have first entropy decoder followed by an inverse transformation. Now, for the forward transformation, since we have chosen an orthonormal matrix, the reverse transformation matrix is nothing but the transpose of the forward orthonormal matrix. So, with this we come to the end of our study of transform coding, and also we have reached to the end of our course on information theory and coding.